Piskunov, and on behalf of the Crafoord Committee for Astronomy of the Royal Academy of Sciences, I would like to present this year's laureates. So this year laureates are Professor Douglas Gough from Cambridge University in the United Kingdom, Professor Jørgen Christensen Dalsgaard, Aarhus University in Denmark, and Professor Connie Arts, Catholic University of Leuven in Belgium. The citation formulated by the committee is for developing the methods and applying them to the sun and other stars. But what I would like to take a couple of minutes to talk about is something that did not end up in the citation. Astronomy is a very old science, and similar to some old people, it has developed a number of preconceptions and pessimism towards any new development or some new development, and in particular the fundamental development such as looking inside the stars. To illustrate the situation and the overall understanding of the situation with stellar interiors, I would like to bring up the citation from a very famous, probably one of the most important astrophysicists of the 20th century, Sir Arthur Eddington. In the introduction to his book about internal constitution of stars, which was published about 100 years ago, he wrote, "Our telescopes may probe further and further in the depths of space, but what appliance can pierce through the outer layers of a star and test the conditions within?" So you understand that our laureates had a very steep uphill battle to get the method recognized. And so not only did they have to develop a new method, but also demonstrate that it works, and not only on the sun, because then it will be a more exotic case, but on the other stars. And so that understanding of all this complexity and challenges, and the fact that our three esteemed guests managed to succeed is what lies behind the decision of the committee to award this prize. Of course, we can talk about philosophy of science and then discuss that certain problems cannot be resolved by frontal attack. And of course, that's what Eddington was referring to. He was referring to conventional observations of light and spectra of stars and the sun, which did not bring the information directly about the conditions in the interior of the sun and of other stars. And so listening to those objects instead of looking at them was the solution to the problem. As I already mentioned, the important and crucial achievements by the laureates was not the seismology as such. Seismology was already a pretty actively used tool to probe the interiors of the Earth. But the concept of transferring it to stars where there is no solid surface, where we cannot actually generate the source of sound, was not very obvious when this whole work started. And the other thing was generalization of this method that was demonstrated for the sun to other stars. Because, of course, for the sun, we see the surface of the star and we can have time information and spatial information, while for other stars, we don't have spatial information. Among the beautiful results that was the consequence of this development, of course, one should mention solar neutrino problem and the reconstruction of the internal rotational profile of the sun. Just short, to conclude my presentation, the short history of the achievements and discoveries. So interior structure of the sun, roughly 1981. The measurements of the depth of the solar convective zone and discovery of tachocline, 1991. Differential rotation and transition to solid rotation in the stellar interiors confirmed with multiple very accurate measurements for the sun, 96. The role of magnetic fields, maybe around 98. First applications to other stars around 2002, and then systematic stellar surveys using astroseismology and space missions starting around 2008 and ongoing, actually. To the very final point is to illustrate how active and popular this research is today. I've looked at the ADS and found 400 papers, more than 400 papers dedicated to astroseismology or using astroseismology published just in 1 year in 2023. Thank you.
You're going to hear today from the three of us about the seismology of stars and the results, some of the results, so many results. If there were 400 papers published last year, we can't discuss all of them. I will discuss none of them. I'm just going to give you a very, well, my wife won't agree with this, I was going to say simple, explanation of the kind of methods that are used to make the deductions, and I'll only mention one or two of the conclusions, leaving it to my two colleagues to go through the really complicated stuff that's come since. As you've just been told, astronomers are a bit stuffy. They normally don't do much other than look at the surfaces of stars. They just measure the stars on the outside and make assumptions that the inside is probably the same. We seismologists, and the reason for that is that the stars are opaque to light, but they're not opaque to other things, and in particular, they're not opaque to sound. Those are oscillations that go on inside the star, like in a musical instrument. There are other waves, many other kinds of waves, that can also take place inside stars, which I just won't go into. They're transparent in some parts of the star, but not in others. The reason we started out with acoustic waves, and the reason for that is that they travel right through from the center to the surface of the star. So what we do is we measure the inside of the stars, and as it's just been explained to you, this is a new thing to do. And by new, I really mean the last half century. But we still have to do it by looking at the outside. We can't hear stars, in particular the sun, which is where we started. And the reason for that is there's no air between us and the sun, and so the sound waves can't propagate. If they could, we wouldn't hear it, because the pitch is too low. As a musical instrument gets bigger, the pitch gets lower and lower. The sun's a pretty big musical instrument. Well, sorry, it's a big generator of sound. I don't think any musician would say it's a musical instrument. It sounds a bit of a mess. But we can only do it by looking at the surface, looking at the motion of the surface. And so we have to do that. But it said there, by looking at the outside. And we do that by looking either at intensity fluctuations or velocity fluctuations, which are measured by the Doppler shift. So just to start off with, I want to give you a very rough picture of what a star like the Sun looks like. It's got a central core where nuclear reactions are taking place, and that provides all the energy. We now know that. We didn't know it originally. And then there's a region outside. We call it the radiative core. Oh, I can see it here. I don't have to look up there. That's great. We don't have to... the light can start getting out. But near the surface, it gets pretty foggy, and it's difficult for all that light to get out. The heat gets dammed up in the middle, and it turns over in what we call a convective zone. And different properties of models of stars like the Sun will give you different depths of the convection zone and different structures. That's not true of all stars. It's just true of the simplest of stars, like the Sun. And I'm going to stick only to the simplest of stars. You're going to hear a terrible mess of complication from Connie at the end of the morning. Oh no, the beginning of the afternoon. Okay, so that's a picture taken from a spacecraft, a Michelson Doppler imager from Stanford, of the Doppler shift from the Sun. It's not the complete Doppler shift. I haven't got time to go through all that. The Sun's rotating, and that's the dominant effect. You take that out. And then if you average over hours, you then get the top of the convection. Convection wells up and goes out sideways. So there's not too much in the middle because it's going horizontally, but at the edge it's coming towards you. And that dominates, that's the next part of the signal, dominates. So we take that out and then take a photograph of the Sun, well, not a photograph, but and subtract all that stuff. And this is what you end up with. And this is the vertical motion. By vertical, I mean in the direction of gravity. And so you see its greatest amplitude in the center, lowest at the edge. And because it's the line, what we measure, of course, with the Doppler shift is the line of sight velocity, not the vertical velocity. So we take this and then we try to analyze it. And we analyze it with spherical harmonics. We project onto spherical harmonics just in the way you might take a Fourier transform in one dimension. On 2 dimensions on the surface of a sphere, they're spherical harmonics. And the spherical harmonics, as you probably know, are orthogonal on the surface of a sphere. So you could actually follow all the motion, describe it all that way, except that we don't see the whole surface of the sphere. We only see one side of it, and the edges are a bit difficult anyway, so we only get about a third of it or a quarter of it. So therefore, we can't separate everything very cleanly. And that's one of the problems that has to be overcome. Now, that's just an example of a particular spherical harmonic, or particular 3 examples of a particular spherical harmonic. The quantity L, that's that vertical line, a horrible font there, is a measure of how many blobs there are over the surface of the Sun, depending on its shape. Those are 3 examples of when L equals 6. And you see the first one, which is symmetric in direction. That's the lines where there's nothing, where the nodes are cones, and there are 6 such cones. And on the one on the right, they're only varying around the equator, and there are 6 slices you can draw through the model, through the picture, and that's the one on the right. If the Sun were rotating, the one on the right will be giving you an oscillation related to the rotation too, whereas on the one on the left won't tell you anything about the rotation because it's symmetric. The one in the middle is a mixture of the 2. It's got some cones, some planes cutting through, and there are 6 of them if you count them. So it's all 6, and if the Sun were a perfect sphere, and this is a property of these oscillations. The oscillations are quite small. And so therefore, one can linearize the equations of all the motion and set up a linear set of equations describing this small motion. And it ends up just like, for example, looking at a hydrogen atom in quantum mechanics, which a lot of physicists are more familiar with. We're not, because we learnt all this stuff before quantum mechanics existed. No, well, sorry, the subject got understood before that. I wasn't around, nor my colleagues. What was I going to say? I've even forgotten. So what I was going to say, therefore, a spherically symmetrical model, a spherically symmetrical star, wouldn't know the difference between those three modes if it weren't rotating. And so all the frequencies are the same. But given that the star's rotating, the frequencies of the one on the right will be slightly different from the one on the left, because the one on the far left doesn't change, the one on the right does. And so from trying to understand that, we can learn about the internal rotation. We now also want to know about what goes on the inside. And so for that, I'm going to have to show you a little bit more, but not too much. These are standing acoustic waves. Just like in a musical instrument, waves go along, turn around, come back. If the frequency is such that the wave number fits exactly into the machine, into the instrument, then we get resonance. And then that dominates by an enormous amount the energy that is then produced, or the energy that exists in the oscillation, and that gives you the tone. And so that's exactly the same in a star, except that it isn't straight. It's a bit of a mess. Well, not a bit of a mess. It's quite simple, actually. Rays might go down, they get refracted and come back up again. And how far down they go depends on which way they're pointing to start with. The oscillations on the sun, which are observed, only have quite a narrow frequency range, factor of 3 or so, maybe a bit more, depending on how well you can see the edges. But in terms of the value of L, it's 1,000, or depending on how you count, you can consider it to be even more. So forget the variation of frequency at the moment, just to make life simple. It just depends on the angle at which it's going down. And so these are examples of the paths of sound waves that are all produced at the point A. It's the path. You should really consider it not as a line, but as a thin tube. And the lines are going through the middle of the tube, and it's telling you how that tube goes down and then comes up. And then you could imagine another one that's obtained by rotating the whole thing, the whole pattern of nodes a little bit further round, and again a bit further round, and you can fill the whole of that area down to, I can't point. I can point a bit. Down to the base at which it comes. So the blue curve, I mean, will depend on everything going on out here. The green one, everything going on out here. And there are lots of them. So if you average over what you see, then you get a picture which is, I've got it here. Those example, the brown and the red are examples of two such waves. And the shading is the average of how the interior of the sun determines the speed at which things are going. It depends upon the time taken for the rays to, roughly, for the rays to pass from one level to the next. And so the time taken right at the bottom is much longer because it's traveling horizontally. On the other hand, of course, it's traveling faster, so that there's partly a counter effect. But you can calculate, if you knew the sound speed all the way from here to the base of where the waves are turning around, then you could calculate the shape of these curves. Here, if you didn't know anything more, you could calculate the shape of this curve except for the very bottom. But if you knew the frequency, you could then estimate what's happening on the bottom and then get some information about what's happening. So what you would do is subtract one from the other, and then you get this curve on the right. Brown minus red, as you all know, is green. And so that's what's left. And the outside, of course, almost cancels, and you're left with a ring, bright ring which is giving you the information of the difference between the frequencies of those two modes, once you've done the calculation carefully. But what we actually do is use thousands of modes instead of just two. We do it more carefully, it's more complicated, and so we can get rid of all this stuff too and try to concentrate in a very thin region. And this is an example measured as a function of the radius of the star. This is an example of the sensitivity that we can achieve. Depending on how many modes we've got, we can't get it infinitely narrow, but we can get that kind of sensitivity. In fact, that's an old picture. Today we can do even better than that and make it even thinner. Can't go too thin, because in constructing these differences, there are always errors in the data, and there are always possible errors in the theory. And those errors, you don't know what sign they are, so once you've put together a very large number, the errors get bigger and bigger and bigger. In fact, you must realize that I was telling you how you can go deeper and deeper by looking at more and more modes. But what you infer from the mode penetrating most deeply depends on on everything, what happens above it. And what we've learned, what happens above it, is subject to all the errors you've made. So the effect of the errors gets greater and greater the closer you get to the center. So it gets harder and harder and harder to get to the very center of the star. Rotation, you can measure, as I said, by seeing that pattern go round, and then use the same technique to go in, to get inside. But I should point out that the difference in the frequency due to the change in the frequency due to the rotation is about 1/1000th of the frequency itself. So getting the rotation is 1,000 times harder, you might think. It's probably even harder than that, actually. So it's not an easy thing to do. But we've made some progress. Now, I'm just going to mention two problems that were in my opinion, the most important unsolved problems when helioseismology started. And they've already been mentioned by Matt. I think it was just now. Oh, no, it wasn't. It was you. Sorry. Namely, the amount of neutrinos produced from the nuclear reactions in the core, because that was to be a direct test of nuclear physics, and the effect of rotation, which causes the sun to bulge, which changes the gravitational potential around the sun, and hence changes the orbits of the planets. And even at the beginning of the 20th century, it was well known that there was an error in the calculation of the precession of the orbit of Mercury after taking account of 99%, I think it was, of the effect of the perturbations of all the other planets. There was left a discrepancy of 43 seconds of arc per century. And that was thought, well, it was originally thought there must be another planet, but we know there isn't now. A planet called Vulcan, which was inside the orbit of Mercury. And Vulcan was discovered observationally. But then other observers couldn't see it, so we now believe it doesn't exist. This happens in science, of course. If you really want to look for something, sometimes they get found, even when they're not there. So one has to be very careful in interpreting. I would say I'm a theoretical observer. I have to look at what the observers tell me and ask myself, do I really believe that? And that's not always the case. Although in this case, I believe everything you say, Connie. So I recommend you don't think that way in the talk this afternoon. So this is a picture very similar to the one you've seen just now. This is the rotation of a segment of a quarter of a slice through the sun. The other side would be the same, of course, but coming towards you rather than going away from you, perhaps. And the southern hemisphere would be the same. And one of the reasons for that is that by the methods I've just been describing, you could only measure the north-south average of the rotation. And so therefore, if it were very different from this, because the north and south were very different, this would be the average, and we have to use other techniques, which I won't go into, to see whether that symmetry exists. But red is fast, blue is slow, and it's been well known for a very long time that if you look at the surface, the equator rotates quite a bit faster than the poles. But this dotted line is the base of the convection zone, which we can learn from, well, I'll show you soon, learn from measuring the sound speed as you go inside. The inside is almost rigid. I mean, that's the slight difference between orangish and yellow are probably uncertainties, because I told you the errors magnify enormously as you go deeper inside. So that's probably meaningless. It's probably, you might think from this, uniform rotation on the inside, but quite varied rotation on the outside. Those of you with good eyes can actually see what the colours mean. And those are in units of, I can't remember, nanohertz. So we have that picture now. And one thing we might want to do is it's not just get that, because, you know, the best astrophysicists are really physicists. I consider myself to be a physicist. And so the important thing is, what would you learn about physics from that sort of picture? But I'm not going to discuss that today. There isn't time. This is just repeating what you've just seen, but plotting the angular velocity as a function of radius just from the outer 50%. And so you can see that, and these are different latitudes. So you see at the low latitude, the high latitude, it's going slowly. The equator at the top is going faster. And then they all collapse into something that looks almost uniform. But we don't really know at this point that it's uniform. And the actual value of that point is a little uncertain at the moment. But from that, you can actually do a calculation. Having learned something about the internal structure of the star, which I haven't yet shown you, but accept it for the moment, you can then calculate how much the sun bulges as a result of the rotation, the centrifugal force from the rotation from this picture. And we're going to have to assume that it goes uniformly all the way to the center. And if you do that, you can then get a value of that bulging, and you get a number which might well be, oh no, not yet there. I remember now, I've told you there's a great deal of it, the uncertainty gets greater and greater as you go into the middle, and at the moment I'm going to assume it's uniform all the way to the center. We have some very bad observations. They're not, sorry, they're good observations, bad deductions from them, because that it looks as though it's pretty well uniform, except perhaps very close to the center. So you need to know how sensitive this curve is in producing the bulging, the oblateness of the sun, as a function of distance. And that's plotted in the next picture, this white line here. I've plotted it against the setting sun, because the setting sun looks typically rather oblate, flattened. But that flattening is really pretty well all due to the Earth's atmosphere and refraction, and not the shape of the sun itself. But this was published in a popular journal, and they wanted a popular picture. But you see, this curve is quite low near the center, so the fact that we've made some assumptions about what's going on in the center doesn't affect the final result too much. There have been theories of gravity which have predicted things like the rate of precession of the perihelion of Mercury. But the first successful one, I think, was Einstein with his general theory of relativity, and that fitted exactly on the assumption that the sun was a sphere. But we know the sun's not a sphere, so is it now bulging enough to destroy that result? And there have been physicists who have said, oh, it must be. And so we've got other theories of gravity that they thought they could then prove. Well, the answer, and this J2, if you expand the gravitational potential in spherical harmonics, J2 is the coefficient of the first term. There's no J1, that would cause the sun to change its the center of gravity. So the lowest one is J2, and this is just about 2 times 10 to the minus 7. So that's how oblate the sun is. It's roughly a measure of the difference between the radius at the pole and the radius at the equator, and it's about a part in 10 million. That's pretty round. And that is one of the first results that we got, and that confirms the theory of general relativity, which is an important result, as was pointed out. The other thing that we had to do was look at the neutrino problem, and that you need to learn what it's like inside the sun. So you take these, you do what I do the calculation for the average splitting of the modes as a function of degree, and use the technique I sort of outlined, and then you can get the sound speed as a function of radius. I say sound speed, I mean that's what I call there is the speed at which a sound wave would travel if it were in an infinite uniform medium. It's a nice convenient thing, and we have a formula for that. But the actual waves depend on other things as well. It depends on the way density is changing through the sun. But those are relatively small effects. We have to take them into account. We have to take everything we can think of into account. But I don't want to say how we do that. It's just complicated mathematics. Gets us around that, So I'm going to show you the sound speed. I'm actually show you the square of the sound speed. That's a better one, easier to think about, because the square of the sound speed, roughly, at least for a perfect gas, would be proportional to temperature. So it's roughly gives you some idea of how the temperature changes. And here it is. I was going to say there are 3 curves here, but there are 4 curves, really. 3 theoretical curves for models of the sun, all computed by my good colleague Jan Christensen-Dalsgaard. And the long dashed one is when the sun arrived at the main sequence, and it was a uniform composition because it was believed that it was all mixed up. So the long dashed line gives you some idea of the temperature variation from the center to the surface at the time the sun was first arrived on what we say is the main sequence. The main sequence is when the sun had collapsed, it stops, it's in equilibrium with the energy that's being created by the nuclear reactions in the core, producing the luminosity at the surface. And that y0 because it's the beginning, is the ratio, the amount of helium, the relative amount of helium in the mixture of the sun. The rest to within dirt is hydrogen. So the short dashed line is a similar picture. Oh, no, it's not. Sorry. The continuous line is the same model, but at an age of 4.5 billion years, which is roughly the age of the sun today. And so what's happened is that this whole stuff here has changed a bit. Quite how is a complicated thing that I'm not going to go into. But the thing just to notice is that it now dips near the center rather than goes continuously up monotonically to the center. And the reason for that is the nuclear reactions have turned hydrogen into helium, and that makes the mean mass of the gas greater, the inertia is greater, so the sound speed is lower. And so that's a measure of how many nuclear reactions have taken place over the age of the star since it started. And now the short dashed line is a similar curve, but for a much lower helium abundance. So you can see the difference. And that difference in the helium abundance is certainly no greater, if perhaps quite a bit smaller, than the uncertainty that existed when we first produced a picture like that. Then there's a second continuous curve, which are the results of the observations. And you can see that fits the model with a helium abundance of 0.27 really quite well. And you can only really see the difference in places like this, where they don't quite meet and the line looks thicker. And you can see also we can get very close to the center, but not all the way to the center. It's too difficult to get to the center. I have to make a few assumptions. So that's the result of doing all this. This is now the relative difference between the 2 curves. Well, not those 2 curves, more modern 2 curves. produced by Masao Takato from Japan, and I think the other guy from me really quite recently. And you see that the difference in sound speed is only 0.1% typically. It's tiny. With a nasty-looking finger sticking up, we now know what that is. It's the fact that the theoretical model has a little sharp. It's a bump in the theoretical model, or well, it's not. I say bump. It's a bump in the second derivative of the sound speed, actually, which we can get rid of. Jan and I and a student worked on that. We found a way of doing a bit of mixing of the model to get rid of that term, but the result of the mixing didn't make physical sense. At least that's what I think. And so I would say we haven't solved that problem yet. And then there's a broad difference that is, as I say, not solved yet, but is pretty small. It's a part in 10 to the 10 cubed. This is the same picture for density. It's harder to get the density. I told you it's not just sound speed. It depends on something else. It depends on any other independent thermodynamic variable. So we chose density because it's something easy to think about. Those are bigger numbers, but they're still pretty small. So we can do quite well. Now, I want to finish. What's the time? 1 minute left. Oh, I haven't seen you up there. You should have shouted at me. Well, I'm going to stop now then, pretty well, since I've only got a minute left. Just to point out that that bump you saw, which is at the base of the convection zone, and another couple of bumps that exist in the sound speed resulting from the ionization of helium, which changed the equation of state in a thin region. Those little bumps take place on a length scale which is much shorter than the wavelength of the waves. So you can't think about sound speed and what it does. You have to actually now go and take a different kind of analysis. And what you see, you get oscillatory patterns in the difference between the frequencies and what you calculate. And you can do this just for the very low degree modes, the ones with almost no variation over the surface, only a slight variation. And the reason we did that is because you can do that for other stars. And so it's a beginning of asteroid seismology. What I showed you before required a knowledge of a wide range of degree, which we can't do on other stars. So we're not going to get a picture like the sound speed I showed you from other stars. But we can do something, and I'm not going to tell you what that is because my colleagues are going to tell you in great detail. But I just want to say that these little bumps coming from the ionization of helium and from the bottom of the convection zone, where there's a discontinuity in the second derivative of sound speed with respect to radius. And we can measure things like second derivatives these days. The results are so good. That we can now attempt to model, to take models and fit them to a large amount of data. We know the smooth variation of the frequencies of the low degree modes as an expansion, a mathematical expansion. And we've taken that to 12 coefficients. And then we've got, with the 3 little bumps, each one gives us 2 coefficients. So that's 18. So we have to do a fitting process in an 18-dimensional space. And we've done that. And I can't show you that easily without going through all the other slides. I can whip through it quickly, I suppose. Yeah, that's the result. The age of the sun comes out to be the 4.6 that we believed in the first place. That's the main sequence age. And then people start looking at the age of the oldest meteorites, say, because we believe the meteorites can't be older than the sun. And fortunately, the oldest meteorite known on Earth has an age of 4.567 years. We know that because of atomic decay. So we are safely beneath that value. We are safely above that value, but not by very much, which of course suggests that the oldest meteorites came pretty well at the same time as the sun was first formed. And that teaches you something about star formation, which is important. But the point I want to get across, just to finish here now, is simply that that information came from looking at just the low degree modes, which is all that my colleagues have to talk about. And they can get a lot out of that, as you're going to learn. So the most important slide is the last one, to thank the Crafoord Foundation for instituting this prize and for the Royal Swedish Academy of Sciences for awarding it to us, which is a great honour for us. And as you pointed out, it's a recognition that our subject, to learn about the inside of the sun, is an important measure of the contribution to the world knowledge. And I'd also like to thank my family, or also my collaborators. I've had lots of collaborators, but you'll see probably a picture of Connie's collaborators. I don't have that many. Nobody can beat that. But I've had quite a lot. But the most important is Jan here, who has been a great support to me and a wonderful dear friend. And thank you, Jan. And my eternal support from my family, my children, Russell, Julian, Heidi and Kim. Oh yeah, there they are. I've got 2 grandchildren here, but I've got 7 others, I think. Is it 7 others? So I won't mention all those. The most important is my dear wife, Roseanne, sitting over there, who claims that she suffered a lot because I'm often not there. But that's true of all scientists, I think. But she's a wonderful woman, as my colleagues will assure me. I think I knew that already, but thank you, everybody.